Good morning, everybody. Welcome back to non-Euclidean geometry. Plan for today, we're going to continue our discussion of the Euclidean parallel postulate proof history. As far as office hours go, all my usual ones after class and from 2 to 3 today. I'm not going to have office hours tomorrow because I will be doing break things. But I will be around. I'll be in town for the rest of this week. If you'd like to meet with me later this week after tomorrow, could probably make it happen. Send me an email. We will figure something out. And for giving me homework over Thanksgiving break, perish the thought. Not perish me, not as much as Megan wants it. No homework over there. So, this gave you a hint. Here's what I want to do for the rest of the semester. So after the break, we have one more week of class. Monday and Wednesday, we'll talk about proof of the parallel postulate just a little bit more. That on Wednesday after the break, I'm planning on there being a quiz, last quiz of the semester. And then Friday, the last day of class. Hoo-hoo. I've got a special activity planned that I think you all might like, or not. Next Monday, I will pass back everything that you've turned in so far, including homeworks 4, yes, I haven't forgotten homework 4, and 5, as well as your midterm take-home. Apologize for being so slow on my grading of things. When you have a class of 20 students and it's heavily proof-based, it looks a lot to grade. Any questions or comments before we get started? Why was algebra always so easy for the Romans? Because whenever they tried to solve for x, they always got x equals 10. Okay, so you might recall that last time we proved that, that if we have Wallace's postulate, where Wallace's postulate this is a recall from last time. Wallace's postulate said that if given any triangle ABC and segment DE, there exists a triangle DEF with triangle ABC similar to triangle DEF. What does it mean to say two triangles are similar? Right?
All the angles are congruent, but not the sides.
Yeah, the angles are all going to end up being congruent to each other, but the sides may or may not be. Sort of a weaker condition than two triangles being congruent. And our picture for this was basically hey, here's a triangle, ABC, and here's some other segment, DE. According to this postulate, if it's true, we should be able to construct a new triangle, one of whose sides is DE, that's going to be similar to the original one. So it probably looks something like that, with point F being here. And what we showed last time in class is that Wallace's postulate implied the Euclidean parallel postulate. That if you're working over a Hilbert plane, I should clarify, that if you're working out over a Hilbert plane, you can show that if Wallace's postulate holds, given any triangle and any segment, you can construct a triangle on that segment similar to the original one, then the Euclidean parallel postulate has to hold true. So that's where we left off last time. If we flip to the next page of the packet, I have a question. Does the Euclidean parallel postulate imply Wallace's postulate, do you think? meaning if we're working over a Hilbert plane, where the Euclidean, if we're working over a Euclidean plane, I should say, is it necessarily true that Wallace's postulate has to hold? Right?
I'm gonna go with no.
Why not?
Well, mostly because I feel like we have proven it both directions originally if it was true, and also there's not a ton of room here, and the original proof was really long.
Ah. Fair enough. Any other opinions? Liz?
I'm going to say yes because Wallace seems to work with as long as the IBC axioms are fulfilled and the plane is semi-Euclidean.
In a semi-Euclidean plane, so Euclidean certainly implies semi-Euclidean, as we've seen. And so you think that with semi-Euclidean, that should somehow be able to give us this Wallace construction?
Yes, because it seems that it would not work in a non-semi-Euclidean space, mostly because if where you can have all triangles greater than 180 degrees, where they're not all necessarily the same values. You could have a triangle where it's 181 and then another one that's 182. I would say I don't know if Wallace postulate would still hold in that case, because it's not guaranteeing that it doesn't guarantee that triangles have all equal 180 degrees. So I question whether that would work in a non-semi-Euclidean space.
Yeah. I think we can definitely say that in a space that's not semi-Euclidean, it's also going to be not Euclidean. Mm-hmm. And the fact that Wallace's postulate implies Euclideanness, mm-hmm. a lack of the Euclidean parallel postulate would imply Wallace's couldn't possibly hold true.
Yeah.
So it's definitely going to be the case that a non-Euclidean Hilbert plane could not possibly have Wallace's postulate by what we proved last time. You're just taking the contrapositive of that. So this, by the way, is logically equivalent to saying not Euclidean parallel postulate implies not Wallace. Turns out that Lucas proposed that he thinks it works backwards. That Euclidean parallel postulate likely implies Wallace as well. Whereas Megan, trying to out-psychology me, has proposed that no, because you didn't state it to us originally as an if and only if, and also you didn't give us much room to prove it. Turns out, sorry Megan, you lose. Turns out that, tragic. Turns out that this is an if and only if. That in a Hilbert plane, if Wallace's postulate holds, the Euclidean parallel postulate has to hold. And it's also true that if the Euclidean parallel postulate holds, you can prove that Wallace's postulate has to hold true from that. And the reason why I didn't give you much space, Megan, is because I don't really want to prove that other direction.
Is the proof just like a construction of like a similar triangle, or is there like some weird trick you have to do?
It's a construction of a similar triangle,
Okay.
but it's just not a particularly nice construction of a similar triangle. And it definitely relies not just on the Euclidean parallel property, but also on other properties of a Hilbert plane in order to be able to get some angles. I think, if I remember correctly, I think you have to use side angle side, for instance, as part of that, as well as congruence axiom 1 and 4. So it's not an obvious statement, but in a Hilbert plane, in a Euclidean plane, you always have to have Wallace's postulate holding true. I mean, that face you gave me earlier, that was a distraught face that looked to me like, Dr. Gerstl, I want to parachute. So, here's a question though. Wallace was actually able to prove that this if and only if statement, that in a Hilbert plane at least, his postulate is logically equivalent to the Euclidean parallel postulates. And so the question is, does this solve the proving the parallel postulate dilemma? So Wallace, let's write this down. So Wallace is logically equivalent to the Euclidean parallel postulate in a Hilbert plane. Question then becomes, does this solve the proving the Euclidean parallel postulate problem? The problem of that geometers are working on for hundreds and thousands of years of, hey, Euclid has a bunch of postulates and there's a bunch of properties that we're assuming. We'd like to be able to just not have to assume the Euclidean parallel postulate. We'd like to be able to just be able to prove it from these other results. Wallace comes along and says, hey, here's this perfectly natural result of given a triangle ABC and a segment DE, we can construct it, we can find a point F that makes similar triangles. And Wallace was able to show that with the other assumptions geometers were working with, that the parallel postulate is logically equivalent to his postulate. So does that solve the problem of proving the parallel postulate? You think? Jack?
It depends on whether Wallace's postulate is logically independent from like Euclid's other four postulates, basically. Because if it's not, then we still have the problem of, can you prove Wallace's postulate from like other things?
Yeah, comes down to, okay, so Wallace's postulate has basically just become a fancy way of restating the Euclidean parallel postulate. Can we prove Wallace's postulate? Turns out the answer is going to be no, we can't. Unless we assume something else like the Euclidean parallel postulate along the way. So the answer is, unfortunately, not quite, just because we found a nifty way to restate the Euclidean parallel postulate that happens to look nice. I don't know, you asked me, Wallace's postulate in R2 feels like a pretty natural result, like a pretty reasonable thing, like, yeah, I believe this works in R2. But it turns out that it can't, Wallace's postulate remained unproven from the other postulates. And just because you have a new way of restating the Euclidean parallel postulate, if that new way of stating it, is it something that can be proven, even if it maybe feels a little bit more intuitive in a sense, you haven't really actually made any steps towards proving the parallel postulate itself. You've just found a way to rewrite it using, more flowery language, so to speak. As Wallace's postulate remains unproven from other accepted postulates. Yeah. Any questions or comments about that? Jack?
Were they able to show that Wallace's postulate was logically independent from the others, or they just weren't able to prove it with the others?
They weren't able to show that it was logically independent from the others for a long time, because if they could, then that would immediately show the Euclidean parallel postulate's logically independent. So when the Euclidean parallel postulate, like 150 years ago, was shown to be logically independent of the other postulates, that automatically showed then that Wallace's postulate would also have to be logically independent. Yeah, good question. Yeah. You can prove Wallace is logically independent, and that would actually have solved the problem of can we prove the Euclidean parallel postulate, and that the answer would be no, because if we could, then we could also prove Wallace, which we've shown we can't do. Turns out it wasn't done that way, though. So this attempt to prove the parallel postulate kind of gave us some nice results that was logically equivalent to the parallel postulate. Didn't end up working in the end. So I'm going to flash forward a little bit further into the future and look at the work of Geronimo Sakhiri. Who was a Jesuit priest, lived from 1667 to 1733. Becca, where have we seen this name before? Yeah, Zakiri quadrilaterals, and also a couple of theorems, like Zakiri's angle theorem, Zakiri-Lozandra theorem, basically we've seen him show up in a couple of packets now. But what Zakiri's deal was, is he wanted to try and prove in a Zakiri quadrilateral that all the summit angles are right angles in an attempt to prove the parallel postulate. So in other words, if you recall, what a Zakiri quadrilateral is one where we have the two base angles or right angles, and the sides are congruent to each other. And what Zakiri tried to do as part of his attempt to prove the parallel postulate is he wanted to try and show that the summit angles would then have to be right angles, and then he reasoned that if he could show that, he thought he could be able to then prove the Euclidean parallel postulate from that, if he can show that the summit angles in his own quadrilaterals, in his babies, would have to be right angles. If you recall, what do we know about the summit angles of a Zakiri quadrilateral in a Hilbert plane? We were able to show something about the summit angles in a Hilbert plane. I'm glad Megan and Jack are answering questions. What about the rest of the class? Let's see, what did we know about? What did we know had to be true in a Zakiri quadrilateral about these summit angles?
They'll have to be congruent.
Yeah. We were able to show, using side angle side a couple of times, that these two angles would have to be congruent. And this is something that Zakiri was able to prove. We proved this, that was the first thing we proved in the quadrilaterals packet. So we could say that by side angle side, the summit angles must be congruent. And so Zakiri reasoned, well, we have three cases for if we have congruent summit angles. One of these three cases has to hold true. First case is that the summit angles could be acute. Second case, that they could be right angles. And Sydney, what would that leave as our third possibility for what the two summit angles would be? Yeah, either acute, right, or obtuse. And so what Zakiri hoped to do is to be able to eliminate the cases of acute summit angles as well as obtuse summit angles. He was able to because if you disprove acute, if you show that acute is impossible and obtuse is impossible, then by process of elimination they would have to be right angles. One of these he was able to disprove, the obtuse case, where, if you recall, we actually had a special theorem. We actually talked about this theorem. At least if we assume Archimedes Axiom, then they can't be obtuse by the Zakiri-Lozandra theorem. So the obtuse case proved impossible. using Archimedes Axiom. Or if you recall, Archimedes Axiom was the one that says, given a segment and a point on a ray, you can basically stack that segment on the ray enough times so that eventually you get further away than that point. And so then Zakiri tried for a really, I forgot to mention, that is the Zakiri-Lozandra theorem, which was in the Quadrilateral packet. If you have a Hilbert plane without Archimedes axiom, it's possible to have obtuse summit angles, but then you get a really weird looking space. We saw that happened in spherical geometry, but spherical geometry is not a Hilbert plane, so technically doesn't work as a counterexample. So Zakiri then tried for a very, very long time to disprove the acute case. And eventually, he gave up, and reportedly, he said, the hypothesis of the acute angle is absolutely false because it is repugnant to the nature of the straight line. Which, if you ask me, is the mathematical equivalent of saying, I can't prove that it can't be acute angle. Well, acute angles are stupid anyways. I don't know. That's a quote. That's a quote from the book that I thought was kind of funny. It's like it's repugnant to the nature of the straight line. But the moral of the story is he wasn't able to disprove it. So if he could have disproven it, shown that the summit angles in the Zakiri quadrilateral couldn't be acute, and therefore by process of elimination had to be right angles. I think he could have then gone on to prove the Euclidean parallel postulate. But he couldn't. So he did. And eventually he's like, I don't wanna anymore. It's repugnant to me. The idea that what do you think, Shane? Is the idea of acute angles in the Zakiri quadrilateral being repugnant to him? Does that count as a way to disprove that they could possibly happen? No?
Doesn't seem like it just, seems kind of like a cop-out answer, just.
Yeah, it's a proof by wishing.
Yeah.
I want this result to be true, or I guess in this case false, so therefore it must be so.
Yeah.
Doesn't quite work as a, back in our logic section, there's a reason why we didn't include that as one of our valid proof techniques. Because it's repugnant to suggest otherwise. So Zakiri eventually gave up on trying to prove that the third possibility, that the acute possibility couldn't possibly happen. All right, we've reached the end of the packet. Except not really, because I have a part 2. What do you do? U1, and then 1, 2, 3, 4. So this is going to be a continuation of where the last packet left off. Looking at attempts in history to try and prove the Euclidean parallel postulate and seeing what came of that. So next up we have, I believe it's a French mathematician, Clairaut, who came up with an axiom of something he wanted to assume in order to prove the Euclidean parallel postulate. And I realize as I'm looking at my notes here that I actually forgot to write down the axiom in your packet, which is a bit annoying because this is a very long axiom. Y'all ready for this one? rectangles exist. I lied. That's the axiom. In other words, plural claiming, saying rectangles exist, if you were to be a bit more maybe formal about it, would be to say there exists a rectangle, at least one rectangle, potentially more. There's probably a lot more than one, but there exists a rectangle in space, in two-dimensional space somewhere. Here's his justification for his axiom. We observe rectangles all around us, in houses, gardens, rooms, walls. We see rectangles every day in the world around us, in other words. I'm just going to say we see rectangles all over the place in the world. All right, I think it's a good point to stop for a second, and I'll give you all a couple minutes. I want you all to think about this axiom and his justification for it, and say, what do you all think? So go ahead and talk to your neighbors. We'll just do this for a minute or two here. What do you all think about Clairaut's axiom that there exists a rectangle somewhere in the world, and his justification for it? It's like, oh, we observe them in houses, gardens, rooms, walls, doors. Everywhere we look, we see rectangles, pretty much. How do you feel about that as justification? I see them everywhere. When I close my eyes, they're there waiting for me. With knives.
The window of the he didn't say that they like this exist like by construction. I feel like that's kind of fair. So like if you
But have you heard like the whole like perfect circles don't exist?
if you can just say
It's like I don't know, if you were to say like if I like draw a circle, like, that's all.
All in other words, when you prove parallel lines, that given any line, there has to exist like parallel lines to it. The question is, can you prove that there's no parallel lines?
In order to know that that's trying to be.
But they're like small things that we
Like it's in our mind,
like
we know that it's
remember
right.
when what's the name like maybe microscopic, that's not a rectangle from the naked eye.
And then people are like, oh, we're
We
from
justify one like the theorem.
The other thing is like we had a question. I think it's on like the first homework assessment or something. I forget what was it? It was like
Shoes exist.
shoes do exist, and we can see it. I don't know that whole kind of question.
I don't even remember what it was.
It was. I just didn't have like this is kind of a weird question. Also. Oh yes, if we assume.
You haven't figured it out by now, I love you.
Listen, whatever answer I give you,
Whatever answer you give is going to be wrong.
it's true.
You specifically, or in people or students in general?
Students in general.
Wouldn't that be cool if you could guarantee that the answer to the question that you gave was always wrong? Then you could determine truth by saying the opposite.
Okay, Jack. Is this statement true or false?
The set of all sets that don't contain themselves contains itself.
I was just about to say, or you can look at Russell's paradox for another example.
True. Yeah, so this question was something about the fact that does a line exist, do lines and points exist in every plane? And so my answer to this, which accepted, after Brian accepted it, was that if we assume a plane exists, we're assuming the existence of two-dimensional space. Such a plane must be defined using at least one line.
Yeah, exactly.
But its existence can also be understood using two lines to indicate the two dimensions.
Alrighty, let's come back together and talk about this.
Trunk shape.
So you can say, you make these situations like in your world.
Right.
Yes.
We came up with a way of summing up his justification in 2 words, and that was because Plato.
Because Plato. Okay, you're gonna have to explain that one.
Because Plato was the one where he taught, the perfect form, and it's that, you see the imperfect, that means that the perfect must exist. You see like the imperfect image of a rectangle, therefore the perfect rectangle must exist in mental space.
Because I have an imperfect rectangle, that must mean I had a perfect rectangle in my mind. That must have some form of weird Platonic existence.
Yes.
As a form of the good.
Yes.
Oh man. All right, it's Dr. Arn was here to do mic drop. Have a good day. Strangely though, that was not accepted as a justification. You think it's valid, thing?
Yeah.
Well, not in the way he said it. In that we observe rectangles in houses, gardens, rooms, walls. Is that the ideal form?
At least one of them exists.
At least one of them exists.
That's all he said.
Okay. All right, Megan. Follow-up question. Define existence.
I can see it.
Can you see the ideal form?
He never said the ideal form of rectangle. He said rectangle. No. You can't modify. You cannot modify.
Don't tell me what I can't do in my own class. Let's increase the length of this axiom by 50%.
Now you're changing the axiom.
I'm not changing the axiom. What's the word I'm looking for? Making it clear.
You're making it more specific.
That's not the word either. There's a word I'm trying to think of to like make sense. I'm clarifying. That's the word I'm looking for. I'm clarifying the axiom. I'm not changing the axiom. Becca, what do you all think? Chattering away back there.
I don't think it works. Well, first of all, just because you can't see something doesn't mean it exists. That's like the first thing we're taught in life. Secondly,
There's more to the world than what exists outside your experience.
Secondly, it's kind of like what, like earlier when some guy was trying to rely on a picture to prove something. It's like the same thing.
There's this guy, he's trying to use some picture, he was trying to prove something, you know what I mean.
I don't remember what you put.
I was going to say, could we be talking about Euclid's first postulate in which he's like, oh, draw this circle, whoosh, draw this circle, whoosh, look, they intersect, they have to.
That one. You can't just rely on pictures to prove things. Like we said, that wasn't valid, so then this isn't valid.
Are you claiming walls and doors and
Yes.
houses and stuff are just pictures, they're not actually real?
Yeah, we're perceiving them as a picture.
Ooh, we perceive them as a picture. I was not expecting this conversation to be so philosophical.
Well, it's just a justification. It's an axiom, so you can say whatever you want. Like, Euclid didn't really provide any justification for his axioms necessarily. So if you want to either put this as your axiom or Euclid's parallel postulate, then maybe it makes more sense to say rectangles exist than that there exists a line on the point for any point. There's a single line that's parallel to that.
Or if you're Euclid, even something even more complicated.
Yeah.
Yeah, that's true. I mean, there's a reason why I wrote this as Claude's axiom. He didn't call it that. I don't know what he called it, but I'm guessing he would have called it his, well, I'm going to say his proposition, because it's a justification. I don't know how you would call a proof. Yeah, I don't know how you call that a proof, per se, but maybe just a more of a general justification. Nate?
I was going to say, you could try to do the whole Euclid construction thing, right? Like, oh, look at that cinder block right there, whatever it is, on the
Look at
wall.
that cinder block.
Whatever, the block on the wall is a rectangle.
We had a cinder block hanging from the wall.
Yes, and you could construct a line segment that's that long, and you could construct another line segment that has that same angle, and you can prove it from there.
All right, well, let's try doing that. Let's try doing that. Except let's try and be a little bit better about it. Do we know in a Hilbert plane that a line exists? Alex?
Yes,
Why?
he said so.
In which axiom tells us that a line has to exist?
First one.
First one says if you have 2 points and there must be a unique line between them. How do we know points exist?
Since axiom 3.
Instance axiom 3. I think that one will give it to us. The one that says there exist 3 non-collinear points.
We have at least 3 points.
And then we could combine that with instance axiom 1 to say that we could draw lines between them and there has to be at least 3 lines out there. So we gotta look. We had back in the neutral geometry packet, we said that if this is a point on a line, we can draw perpendicular. Let's say we have 2 points, that we can draw perpendiculars to the line through those points. So we can show we have that. I would argue we could also construct a perpendicular, I don't know, call this, M1, M2, this will be our L. I would also argue that, I don't know, let's pick this. Here's a point on M1. That we could show that there has to exist a perpendicular to M1 through that point right there. Through some line, call it N. Does that prove that rectangles have to exist? Yeah, I see you shaking your head.
No, because it doesn't say anything about the angle between M2 and N.
No! Doesn't say anything about this fourth angle? Doesn't it have to be the case that if we have 30 90-degree angles, the fourth one has to be 90 degrees?
No, because we drew really weird pictures one day to prove that that's not necessarily the case.
Maybe?
Nope, she's absolutely right. We drew pictures and it didn't work.
Didn't work once. Yeah, so we can prove that we can construct, dare I say, Lambert quadrilaterals. Or I could also say Zakiri, if we wanted to do the same construction on this and say, hey, here's a right angle, here's a right angle, pick any point on this line. We could use methods that we've talked about to find a point on this line that makes these two segments congruent to each other. That would be congruence axiom 1 would tell us we could do that. And then here's 2 points, we can connect them. So we could construct Zakiri quadrilaterals, we could construct Lambert quadrilaterals, just from knowing that we're working over a Hilbert plane. The problem becomes, can we prove that these last 2 angles are right angles? Or can we prove that this fourth angle in the Lambert quadrilateral is a right angle? And as we've seen, the answer is, I can't quite prove that just from the axioms of the Hilbert plane. There exist models of geometry, like the Poincare disk, like spherical geometry, where you can have quadrilaterals, like where you can construct quadrilaterals like this with 3 right angles, but the fourth angle is not a right angle. Or where you have a Zakiri quadrilateral where the summit angles are congruent, but they're not right angles. So, even if you're not just looking at some physical object, like Megan's cinder block on a wall, and trying to say, hey, look, it's a rectangle. We know that it can be constructed because here it is, it's been constructed. That's some sketchy proof at best. That's some sketchy logic at best. How do we know this cinder block is a rectangle? All right, I don't have a cinder block here, so let's look at this eraser. Is this a rectangle?
Yes.
Oh, silly, it's 3-dimensional. Rectangles only have 2 dimensions. All right, let's just assume this. Let's just assume this side is this side a rectangle.
Yes.
It is. How confident are you in that? If we zoom in really, 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 really far, can you guarantee we're going to get 4 right angles here
On that specific eraser,
on this specific eraser?
I can shave off the sides of the eraser until it is a rectangle
You can? How are you going to do that?
with a laser.
With a laser? Is your laser infinitely skinny to be able to create such perfect rectangles?
I don't know how lasers work.
Say what?
I don't know how lasers work, so no.
I was gonna say I don't know how lasers really work either, but need to go run down the hall into Dr. Lawback's lab and get her to come over and explain how lasers work for me.
You
I
can
guess
get
not.
a chemical whose bond. This is not relevant. Never mind.
Well, I want to go down the rabbit hole and ask you to explain what you were about to say. I think you can. See, I love getting to be a teacher because it gives me an excuse to play devil's advocate like this all day. You know, the Socratic method, the whole idea behind reductio ad absurdum, etc., etc. I would argue there are no perfect rectangles in this world. That if there were perfect rectangles, absolutely 100% perfect, and when I say there are no perfect rectangles, I mean there are no physical objects that we can point to and say that is a perfect rectangle. We could argue for the rest of the semester if we wanted to about does there exist a Platonic ideal perfect form of a rectangle. But in terms of does there exist a physical rectangle on planet Earth that is a perfect rectangle, I would argue no. That maybe if there were, that maybe there are rectangles so good that we, with our eyes, could not physically perceive them as being, or cannot physically tell that they're imperfect. But if you zoom in far enough, nothing's really perfect.
Is that having to do with the fact that when we're looking at Euclidean plane, we assume that space is infinitely divisible between any 2 points. There is another point, whereas in reality, to the best of what we know, when we zoom in, there are just points and then nothing in between them.
There are
so
points.
You can't zoom in perfectly.
Yeah. How we perceive reality in a continuous way, but if you break it down according to the physicists, reality is in fact constructed of discrete things. Lots of protons and electrons with lots and lots of neutrons and other subatomic particles with lots and lots of empty space in between them. Man, I was preparing this class for today. I was not expecting how much physics and philosophy and metaphysics would get involved in the discussion. But yeah, I would say we could certainly argue this. And all of this, by the way, in the 1700s was something that certainly people were not assuming and talking about. But I don't think we can logically show that a physical perfect rectangle has to exist. Also, riddle me this. Let's see. Let's bring in some geography. John, what type of three-dimensional surface is the Earth?
Three-dimensional surface?
Yeah, what type of...
Sphere?
Yeah, it's a sphere. Do rectangles exist on spheres?
Me?
Since you asked, yes.
Yeah, sure.
Yep. So if I were to draw out a rectangle on the surface of this sphere, you're telling me that I could draw out a quadrilateral with 4 right angles.
I mean, if that's how you define a rectangle.
I'll say defining a rectangle using our definition of lines from class.
And then probably not.
Megan?
That's two things with that. One, that's that's assuming that the Earth is a perfect sphere, which I reject that if you're going to make this rectangle argument. And number two, that's also assuming that you're drawing it on the ground, not necessarily, like you don't, we have rectangles that aren't, yeah, if you draw it in chalk on the ground, like on the sidewalk, then yes, you would get a slightly imperfect rectangle. But if you drew it like, I don't know, on the chalkboard or something, that's not drawing on the surface of this sphere of the Earth.
Yeah, I'm playing a lot of devil's advocate and trying to ask a lot of tricky questions. I would say that argument for, we've shown that Lambert quadrilaterals can't possibly be rectangles on a sphere. The argument's not going to fly for a couple of reasons. One, I agree with you, Megan, that the Earth is not a perfect sphere. And the second is, just because, even if it was a perfect sphere, just because we live on a perfect sphere doesn't mean that everything we draw has to conform exactly to the sphere. But it's interesting. It's something to think about. I love how this is like the sort of class where you can argue for like 20, 30 minutes about do rectangles exist. By the way, you don't get to do this sort of thing in most math classes, but I think it leads to a lot of interesting discussion.
There's the existence of Colorado.
Colorado and Wyoming exist, therefore rectangles must exist. Does Colorado exist?
Colorado exists. I thought Vermont was the place that didn't exist.
Colorado does not exist. And I need to get Dr. Wallace up in here. She's from Colorado originally. Ask her, does Colorado exist? And while we're at it, Dr. Wallace, do you exist? What is existence? So, let's take us on a great aside because it seems like I think we've all had fun discussing this. I would argue that Clairaut's axiom, whether or not we want to agree that rectangles exist, I personally do not accept Clairaut's justification for whether or not rectangles exist. And also, I would argue that, kind of getting back to these constructions that we made here, in a Hilbert plane, we've shown that we can construct things that are Zakiri quadrilaterals. We've shown that we can construct things that are Lambert quadrilaterals. I don't think we have not proven that we can construct rectangles. And in fact, depending on your Hilbert plane, a lot of Hilbert planes, specifically non-Euclidean, or non-semi-Euclidean ones even, I would argue it's impossible to construct a rectangle on. Because constructing a rectangle would break one of our axioms or propositions. Specifically, the proposition that says something about if you have one Lambert quadrilateral that has whose fourth angle is a right angle, then all of them have to. Or the equivalent version for Zakiri. So, we've also actually proven, I'll make a note of this over here because I think this is pretty relevant. If you think back to the last few packets, we've actually proven that in a Hilbert plane, that rectangles exist is logically equivalent to the condition of your Hilbert plane is semi-Euclidean. Or semi-Euclidean is this property of fourth angle in a Lambert quadrilateral is a right angle, summit angles in a Zakiri quadrilateral are right angles, or triangle sums add up to exactly 180 degrees. But semi-Euclidean doesn't even imply Euclidean. We haven't seen a counterexample, but because I said, they're too weird to look at and I don't want to spend an entire week just coming up with one. But there are semi-Euclidean, non-Euclidean Hilbert planes out there. So even if we could show that rectangles exist in our model, turns out we couldn't use that to prove the Euclidean parallel property. We could prove the semi-Euclidean property of, oh, triangle angle sums all have to add up to 180 degrees, but that's not enough to guarantee that we're working with a model of the Euclidean parallel postulate, which is stronger condition, something that's harder to fulfill than semi-Euclidean property. All right, I think that's going to do it for today. When we come back, we're going to talk through Proclus's theorem and Lozandra's theorem, continuing our discussion of trying to prove the parallel postulate. Have a good Thanksgiving, everybody. Hope you all have a good break, get to relax a bit, spend some time with family. You don't spend your entire break working on catching up on grading and your 10-year applications. And have a good one. See you next week.